We can start our session today, and the speaker is Andrey Pilipenko with a talk on a skew stable Levy process. Please.
Okay, thank you. Okay. A skew stable Levy process is a new notion that I will introduce today. At first, let me recall you what is the skew Brownian motion. There are a lot of approaches to the skew Brownian motion. It appears in a book by Ito and McKean, and the definition of Ito and McKean was as follows. Assume that we have a Brownian motion, and we have excursions of Brownian motion. We enumerate them in any measurable way, and then toss a coin under each excursion and select as sign with a plus with a probability P and sign minus with probability Q. For example, if we toss a coin and say minus at this excursion, then we make the following picture. For example, we have minus here. We write this, then maybe minus again, plus, and so on and so forth. Well, if P is 1/2, then we get just usual Brownian motion. If P is 1, then we have reflected Brownian motion. And in general case, this process is called skew. Another approach to the skew Brownian motion was performed by Mykola Ivanovich Partenko, who got the skew Brownian motion as a certain diffusion with generalized drift. So the drift here is delta function at 0 times some parameter, we will say parameter of permeability. Well, certainly there is a question, what does it mean, the generalized drift? I will talk a little bit later about this. Harrison and Shepp proved that the skew Brownian motion is a strong solution to the following stochastic differential equation, where L is symmetric local time of this process X at 0, defined as follows. And well, gamma equals P minus Q if we want to consider Ito and McKean definition. And moreover, Harrison and Shepp proved that there is no weak or strong solution to this equation if absolute value of gamma is greater than 1, then no solution. Walsh in 1978 gave many properties and approaches to skew Brownian motion. He proved that Brownian motion, the skew Brownian motion is a solution to a certain Martingen problem. Also, he explained how to get the skew Brownian motion by some transformations of usual Brownian motion, like space transformation or time transformation, and so on and so forth. And now let us discuss what happens if we want to construct if we want to consider a symmetric alpha stable Levy process instead of Brownian motion. Let me recall you that U alpha is Levy process, so process with independent and homogeneous increments, such that characteristic function of the increment has the following form. Well, we also will consider assume that U alpha of 0 is 0, but oops. But we also can consider U alpha as Markov process. And if I write here X, then I say that, okay, let's consider process X plus U alpha of T. So this process starts from X. It is well known that if alpha is greater than 1, then symmetric alpha stable Levy process hits 0. And the problem is, what is the natural analog of the skew Brownian motion in case of a stable noise? I would like to mention that U alpha of T is a jump process. So it can overjump 0 many times before it hits 0. Assume that we start, for example, from X. And now let's compare. Let us try to use approaches of Ito, McKean, or Pilipenko, or Garrison, Shepp to construct analog of skew Brownian motion for the Levy case. Okay, it is known that Levy alpha stable process overjump 0 infinitely many times before it hit 0. So it is difficult to say what does the sign of the excursion mean. Moreover, when alpha stable process exit from 0, it also visit positive and negative half lines infinitely many times in any neighborhood of the starting of this point when you exit from 0. So this approach does not work. Now let's discuss the paper of Shepp about stochastic differential equations with the local time. And they used Tanaka formula for the local time, and they used some transformation of space, and they considered the process yt that equals phi of xt, where phi is the following function. Here it is a line qx, and here this line is px, where p and q are from Ito and McKean approach. When you apply Tanaka formula or Ito formula, then you get stochastic differential equation without local time, and then they applied Nakao theorem and prove existence and uniqueness to the solution of the equation for y, and hence existence and uniqueness for equation of x. Well, Tanaka formula now is not applicable if the noise is U alpha, and the application of eta formula is very difficult in this case, and actually this approach does not work. There are other approaches for weak solution. For example, like Walsh, he made transformation of space and time for Wiener process, but this method also does not work if the noise is alpha stable. And now let us discuss.
Excuse me,
yes?
can I ask you, you said that martingale problem does not work?
No.
Special form of generator.
I don't say that martingale problem does not work. There were a lot of approaches in Walsh paper. One of them was transformation of space and time, and after this he posed like a martingale problem. But now it is not clear what is Walsh had an object, had this object, skew Brownian motion, and for this object he found martingale problem. But now we don't know what is
the desired object.
Yeah, what is a skew stable Levy process. When we give reasonable definition, we can talk about martingale problem.
I see.
So, and now let us discuss approach of Mykola Ivanovich Portenko, who constructed diffusion with generalized approach, and he constructed a semi-group, and then he proved that the corresponding process is a semi-martingale, and that you have a sum of continuous martingale with characteristic T, which is Brownian motion, and the difference x minus w is an additive functional of x. And then he proved that this additive functional has certain structure. The characteristic of this additive functional was found, and this term was identified in some reasonable way with so it is natural to say that this term is integral of delta function. Indeed, what is local what is the local time? It is the limit of the following, let me write, of the following functionals, and where f epsilon of x is the following function. Indicator of x less than or equal to epsilon divided by 2 epsilon. And in some generalized sense, this sequence converges to a delta function concentrated at 0. The key moment in the construction of this process was a theorem on a jump of single layer potential. And unfortunately, there is no direct there is no direct analog for alpha stable process. However, Mykola Ivanovich and Lobus found some analog of this theorem, and they succeeded to construct a semi-group which that was a perturbation of the semigroup generated by U alpha. Unfortunately, that semigroup was not non-negative. So there is no Markov process that correspond to that semigroup. And now let's look at this formula for transition probability density function of the skew Brownian motion. Here, phi t of x is the density of the normal distribution and 0t. And we may try to write here alpha and say, okay, let's consider density of U alpha of the process U alpha. And it can be proved that there is a Markov semigroup, there is a Feller semigroup that corresponds to this transition probability density function. And actually, Mykola Ivanovich Portenko gave a martingale martingale characterization of this process, but this process does not behave itself as U alpha when the process is in upper or in lower half spaces.
I'm sorry, I have lost. What is phi to the power alpha?
So this is a density. So phi alpha t is a density of U alpha t.
Mm-hmm.
So you can just write this
Yes.
formula by the analogy and say, okay, there is a semigroup. Maybe this is this process behave like U alpha outside of 0, and something happens at 0. Some skewness. There is some asymmetry, some skewness at 0.
Okay,
but the answer is no. This process does not behave itself like U alpha outside of 0. Informally, it seems to me that informally this process can be characterized as follows. We have okay, so this is graph of U alpha t, and so it is a jump process. So sometimes you have over jumps. So at the moment of over jump, you have to toss a coin and to say you go down or you go up to this distance with probability p up and with probability q down, and do this at each over jump of 0. I think that this construction describes the process with this transition probability density function, but there is one delicate moment. The process U alpha sometimes hits 0. So you is closer, and sometimes you hit. And there is no next excursion. So before you hit, you can talk about the next overjump. But when you start from 0, you don't have next. It's like next excursion of a Brownian motion. This situation is the same. So I say that, okay, well, probably this process behaves like, if you consider this construction. And now let me mention one more approach, the approach of Harrison and Shepp in their paper, where they obtain a skew Brownian motion as a perturbation, as a limit of a perturbation of a random walk. Let us consider a random walk with transition probabilities 1/2 outside of 0. So this is symmetric random walk. But when you hit 0, you go up with probability P, and you go down with probability Q. And if you go down and go up, again, you have simple symmetric random walk. And then again, when you hit 0, you go up or down with probabilities P and Q independently of the past. And then they considered the Donsker scaling, and they proved that this sequence converges in the space D in Skorokhod space to a skew Brownian motion with parameter permeability P minus Q. Actually, the proof was very simple. They calculated transition probabilities. They proved tightness, and then they proved convergence of finite dimensional distributions. They also announced the following result, that if we jump up and down by a random variable zeta each time, then the parameter, then in limit you also get a skew Brownian motion with parameter gamma being equal to this. So now we have a perturbation of a simple random walk. We have a perturbation of an object that converged to skew Brownian motion. There are a lot of papers on this topic. Assume that you have random walk and you perturb it in some neighborhood of 0. So Harris and Shepp, Minlos and Zhizhina. I have a few papers with Yura Prihodko, with Alexander Iksanov, with Alexander Prihodko. There is a paper of Ngo and Penier. And usually if this perturbation have a finite moment, first moment, then a limit is a skew Brownian motion. And by the way, you may perturb random walk, but you may perturb Wiener process itself. Let's consider the following model. Consider Wiener process. When it hits 0, then jump. Hit 0, jump again, and so on, and so on, and so on. Let us denote this jump zeta1, zeta2, and so on and so forth. And then make the jumps smaller and smaller. We divide it by n. So sometimes you go up, sometimes you go down. And it can be verified that if zeta has the finite first moment, then the limit is skew Brownian motion, and parameter of permeability is this. And now let us do the same with Levy alpha stable process. Okay, let's try. So what do we do? We consider a process whose increments are increments of the process U alpha. And when this process hits 0, so here you overjump over 0, then you exit from 0 by a jump. So zeta1. Then, okay, you go, then you hit 0. Okay, this is zeta 2, and so on, and so forth. So this is zeta 3, and then makes these jumps smaller and smaller, divide by n, divide by n, divide by n, and the problem is find the limit of this process. And if the limit exists, then I'll call this limit a skew stable Levy process.
Should we divide this zeta, should we divide by n or the some power of n?
No, just you multiply, so you may multiply this by epsilon, so it's all the same. No, what do you mean?
I mean that instead of n, probably one should consider power of n to the power.
Not the power of n. No.
Okay.
Look, if you write, okay, this is a reasonable equation. You may write here n to the power beta, but okay, if x zeta over n converges to some process, and n is not a natural number, just positive number, then this sequence also will have the same limit. And I consider convergence only in distribution. Because, well, just replace n to the power beta by m and say, okay, we consider sequence x zeta divided by m, and if n converges to infinity, then m converges to infinity. So it is all the same to write here n or n to the power beta.
And it does not matter which distribution has this zeta?
Zeta, no, it matters. It matters. So the question is, okay, let's make some perturbation. And now let us think what is a reasonable perturbation. And now let us discuss what is this process. This process at the moment t equals increment, sum of increments of u alpha t. So u alpha t plus sum of jumps from 0. So u alpha of t plus sum, so number of visits to 0 of this process, zeta k divided by n. Okay, this process just equals u alpha, so converges to u alpha of t. So if we want to have a limit of this process, then this term should converge. And what do we see? We see the sum of random variable scaled. So it's natural to assume that zeta belongs to a domain of attraction of a stable law.
Now I see, thank you.
Yeah, so this means that there are some constants an and bn such that the following sequence converges in distribution to a non-degenerate random variable. Or maybe we also will assume that maybe zeta k just have finite expectation. Now let me comment. Let me make some comment. When we consider some limit behavior of random walks, for example, in Donsker theorem, and when we study the number of visits to 0 or the number of crossing 0, then, and if we normalize this functional properly, then this number of visits or number of crossings will converge to a local time of the limit process, to some local time. And now we have some expression, sum of zeta k's divided by something.
Sorry,
And
one more question.
yes.
Sorry for interrupting. So this zeta has are in the domain of attraction of a stable law with index alpha or with some other?
No, maybe with
any-
another,
Okay.
say with index beta,
Okay.
another.
Okay, I see.
Okay, assume that zeta k belongs to another, to domain of attraction of another stable law. Then if you consider the following process and okay, divide by proper constant, then this process will converge to beta stable process. So my conjecture is the limit of this term will be this object, u beta of the local time of the limit process. And zeta k's are, so we suppose that they are independent of u alpha. So this u alpha and u beta will be independent. Well, there are a lot of questions. What is the local time? How to prove this convergence? You see, we don't have a process. We have at first to prove that the limit exists and then discuss local time of the limit. And my next question is how to prove convergence of stochastic processes. When we considered skew Brownian motion and perturbation of skew Brownian motion, there were different approaches. For example, Harrison and Shepp, they just calculated finite dimensional distributions. Actually, Ngo and Pengier also, they got some estimates for finite dimensional distributions and pass to a limit. Just so this is a classical approach. But if the noise is alpha stable, then I think it is very difficult to find or to estimate these distributions. We also used some probabilistic technique. Alexander Alexanov, we used martingale. We solved martingale problem. Minlos and Zhizhina, they used semi-group approach, and they proved that semi-groups generated by a perturbed random walk converges to a semi-group generated by a skew Brownian motion. And now let me apply another technique that is based on Resolvents approach. There is a result, I found it in a book by Etier and Kurtz, that if you have uniform convergence of resolvents of failure processes, and the limit is also a resolvent of a failure process, and if Xn are Markov processes whose resolvent is Rn, and if sequence of initial distribution converge to random variable x0, then we have convergence of the corresponding failure processes in Skorokhod space. So now let us calculate resolvents of perturbation of alpha stable process, and then try to find the limit. But I want to make one important remark, that when we consider this process with jumps, this process cannot start from zero. So at the moment of at the hitting moment, we jump, and our perturbations never equal 0. So the phase space for our perturbation is R without 0, and this is not good. Certainly, there are some theorems, some generalization of this theorem, but it is okay. It is not straightforward what to do and how to calculate resolvents. We have to consider different phase space R without 0 for prelimit processes and R for limit. And let us make the following. Let us do the following trick and consider so-called holding and jumping processes that are constructed as follows. When you hit 0, you spend some exponential moment at 0 and then jump. Then you hit 0 and then spend again exponential time at 0 and then again jump. And let these jumps be zeta1, zeta2, and let us assume that this m is large enough. And actually, this holding and jumping process is Markov process, is a Feller process, and it's easy to calculate resolvent for this process. And let me recall you Slutsky lemma that if xn and yn are sequences of random elements in a metric space such that distance between xn and yn converges to 0 in probability, and if xn converges in distribution to x, then yn also converges in distribution to x. And if m is large, then distance between the process without holding and the process with holding converges to 0, where d is a distance in Skorokhod space. So if we prove that this sequence converges to some process and mn is sufficiently large, then this sequence also converges to the same process. Well, now let's calculate resolvent for this process. The following calculations are just general calculation for a Feller process that hits 0 with probability 1. So let me recall you that resolvent is the following expectation. I also will consider resolvent of the process killed at 0, and sigma is a hitting time. Sigma is the moment when the process hits 0. So we start from x. So this is sigma, and this integral can be written as integral from 0 to sigma and then from sigma to infinity. And the first integral is just resolvent of the killed process. And for the second integral from sigma to infinity, let us make a change of variable. And if the process is strong Markov, and our processes are strong Markov, then we see that this process is independent of this, and the process x of t plus sigma has the same distribution as the process that starts from zero. So we can write here product of exponents, and here you just start process x from zero. And now look, this is resolvent of the process started from zero. Okay. By the way, when we consider processes with this holding and jumping processes, then the first part before the heating is the same. This part is the same as for alpha stable process. So this term will be the same for all holding and jumping processes. And this term also is the same for all holding and jumping processes. So we need only to know the distribution of this functional for alpha stable process. Well, we are going to prove uniform convergence of resolvents. So in order to prove uniform convergence, we see that we have to prove only a convergence of pointwise convergence of resolvents at zero, and that's all. And now we have this representation. So let us try to find resolvent at zero of holding and jumping process. And again, the calculations are just general. So we start from zero. We spent at zero exponential time with parameter m. And then we jump, then we walk, and so on and so forth. Let us represent the integral as sum of two integrals. And on this interval, the process x of t just equals zero. So we have f of 0, integral from 0 to t1 e to the minus lambda t times f of 0 dt. And this integral equals this. Then you jump and start from the point zeta. And again, you apply strong Markov property and so on and so forth, and get this answer. Tau1 has exponential distribution, so you can calculate this expectation and this expectation. So you have that the resolvent at 0 equals something plus integral of resolvent with respect to distribution of zeta. And now plug this here, and then integrate with respect to distribution of zeta. When you do this, you can find this term. It appears in the left-hand side, and then you find this. You again plug it here and obtain the following answer. You obtain the following answer for holding and jumping process. And now we assume that m converges to infinity, and we divide zeta by n. So this, and we assume that mn is very, very, very large, as larger as possible. So to find the limit of this, we just have to find the limit of this ratio. And let me recall you that we assume that zeta k belong to a domain of attraction of a stable law. I will also assume that beta is between 0 and 1, or I also will assume, or maybe that expectation of zeta is less than infinity. Well, if zeta k belong to domain of attraction of a stable law with index beta, then there are then tails of zeta have some regular behavior. And let us consider the following measure. And the result is the following. The limit of resolvents of holding and jumping process equals the following if where eta is the following measure, or if beta is large enough or expectation of zeta is finite, then the limit of this just equal resolvent of symmetric alpha stable process of our initial process. And the first result of my talk is the following. If beta is greater than alpha minus 1, or if expectation or the first moment of perturbations is finite, then sequence x zeta over n converges to alpha stable, to the process u alpha. So the limit is just our initial process. So so this means that perturbations are very, very small. If beta is less than alpha minus 1, then the resolvent of x of the limit process is equal to the following expression. Okay, from the previous theorem, we see that the limit is this, and this is a question: is it a resolvent of a failure process? And the answer is yes. You may find so I found this in Blumenthal's book on excursion of Markov processes. And he considered not only alpha stable process, but some Markov processes that hit 0 with probability 1. And eta was some measure. So the result in the book of Blumenthal was the following. If you have a failure process that visits 0 with probability 1, and if eta is infinite measure that has some properties, then this is, and sigma is just hitting time of that Markov process, then this is a resolvent of a failure process, and this failure process outside of 0 behaves itself as original Markov process. So, and he says that this process is in some sense a recurrent extension of original Markov process killed at 0. A few words about the proof of the convergence of resolvents.
I'm sorry, this was the statement in Blumenthal-Gettur?
In Blumenthal-Gettur, the statement was that this is a resolvent of a failure process.
Yes, yes.
Yes.
Killed after and then resurrected.
Yeah, of some. Yes, he has some how to say some characterization of this process via eta excursion theory. But the question is, what does it mean for our alpha stable process? And okay, I would like to show some useful formulas and a sketch of a proof of convergence of resolvents. Well, it's known that the resolvent kernel for the process U alpha has the following form. And actually, if x is 0, the integral can be calculated. And the resolvent of the killed process satisfies the following property. So this is just a general fact for arbitrary Levy process. And again, this is just a general fact for Levy process. And here should be written minus x. Well, for our Levy process, this function is symmetric, so we can write plus x. And moreover, the asymptotic of this integral can be calculated. So after some transformation, we have the following. This integral, this expectation, is equivalent to x to the power alpha minus 1 times some constant. Well, and this constant can be calculated too. And now, let me consider only the case when perturbations are non-negative for simplicity, and let G be a distribution function. We have to find this limit or this limit, and it is known that if zeta belongs to domain of attraction of beta stable law, then you have the following. So divide here numerator and denominator by 1 minus g of n, and actually here eta is the measure dx over x to the power 1 plus beta with this distribution function. Okay, with whose tail is the following. This measure is infinite, so please be careful. This is not a probability measure. And if beta is less than alpha minus 1, the following general fact can be proved, that the following limit equals this integral. We know that, okay, this converges pointwise to this. So it is reasonable to expect that you have this formula. And the function, well, the limit measure eta has the following density, dx over x to the power 1 plus beta. So you may have problems at 0. This measure is infinite in a neighborhood of 0. But if the function g of x is too small, then it can be proved that irregular behavior of this measure at 0 is negligible. And actually, beta should be less than alpha minus 1. So this is critical and actually very reasonable critical level. If you have this inequality, then it appears that, okay, this function behaves like x to the power alpha minus 1 in a neighborhood of 0. Then it can be proved that the main part of asymptotics is the ratio of numerator and denominator in the neighborhood of 0. And in order to consider the case when beta greater than alpha minus 1, at first we have to study convergence of v lambda of f over v lambda of 1 at the point x. Well, it can be proved that this ratio equals lambda times resolvent of non-perturbed or alpha stable process and if tails of zeta has behavior like on the previous slide, like this, then it can be seen that in this asymptotics, behavior of this ratio, is the most important term when we calculate this limit. Okay, and probably the last result that I want to announce is stochastic differential equation for the limit process. It can be proved that the limit process is a weak solution to the following stochastic differential equation. Xt is initial condition plus the process u alpha plus the process u beta, beta stable process of the local time of the process x, and this process u beta is beta stable process with Levy measure, with the following Levy measure, and C minus and C plus are constant from tails of zeta of the random variable zeta, and the constant C here equals this. And moreover, the limit process spends 0 time at 0 with probability 1.
Andrey, can I ask you the following question? You didn't say anything in this stochastic differential equation about the probability dependence between U alpha and U.
They are independent. Sorry, they are.
So we just
which is independent of U alpha. So they are independent.
So we initially can say that let we have two independent processes, then there exist or we can build on other.
Yes, there exists probability space such that we have this representation. Exactly.
Okay, thank you.
And maybe a few words about references. So this is a paper of this is a book of Ita McKean. This is a paper of Nikolai Ivanovich about diffusions with irregular drift, where he constructed, for example, skew Brownian motion as a diffusion with singular drift. This is a paper by Harrison and Shepp on strong solution of skew Brownian motion. This is a paper of Walsh on martingale characterization, and actually in this paper Walsh introduced his Walsh Brownian motion. This is a paper of Mykola Ivanovich Partenko, where he characterized the Markov process whose transition probability density function was as follows. But here phi is a density of u alpha t, not of a linear process, but of u alpha of t. And these two papers by Lobus and Portenko and Osipchuk and Portenko, where they constructed semigroup and where they got analog of formula on a jump of a potential of single layer. And these are books by Blumenthal and by Etienne Kurz, where I found references for convergence of resolvents and for description of the process with certain resolvent. I also want to say many thanks to Mykola Ivanovich Portenko for very interesting discussions on this topic, and Mykola Ivanovich explained me a lot about semigroups, additive functionals, heating times, some approaches of construction of diffusions with singular drift and so on. Okay, that's all. Thank you.
Thank you very much. Maybe some comments or questions, please.
I have small question.
Yes, please.
So concerning this last SDE with dx equal u alpha plus u beta of local time of x. So if we replace u alpha by Brownian motion, what I guess something you will be also. Or?
What do you mean? Yes, the result will be the same. If you, well, the result is the following. If you consider okay, if you consider,
I mean, your result is for alpha strictly smaller than 2.
Okay, okay, the result is the following. Assume that, consider a process with the following resolvent, where V lambda of f is resolvent of Brownian motion killed at 0. And sigma is heating time of 0, and eta is the following measure. Then the process, this process satisfies the following equation. Here you have to write linear process, but well, maybe with square root of 2, because for linear process characteristic function is minus z square t over 2, and for Levy alpha stable process I wrote that characteristic function is like this. Yes, so
alpha equal to 2, everything is okay.
Yes, everything is okay.
Maybe other questions, please.
I have one question and some comment.
Okay, maybe you will begin with question.
Okay. If you consider skew Brownian motion, then it is easily to show that if the process started from 0, then the probability that it occurs on positive half line is exactly that p in the theory eta Maki, and at any fixed moment of time. Okay.
Yes.
Starting from 0, x of p is positive, equals this probability equals that parameter p in Ito and Makin theory. And,
yes.
Okay. Is it possible to calculate such a probability in your situation?
Yes.
And what?
Okay, so let me explain you. One moment. So there is another description of my process via Ito excursion theorem. Let me explain you what does it mean. Okay, let us start with some Markov process that hits 0. Okay, maybe sometimes you have jump exit from 0. So excursion is a part of trajectory between zeros. Roughly speaking, the part of excursion between zeros. And how Ito constructed extension, how Ito constructed Markov processes. He considered a Poisson point measure in a space S times D 0 infinity. So now point is a pair S and X. X is a function. So let me write, okay, like function. So I cannot, okay, this is infinite dimensional space. Well, and intensity, assume that intensity is ds times some measure d dx. Assume for a while that p is finite measure, and let us make the following construction. You find the first moment, the first atom of this Poisson point measure. You have here some function. Well, and this function that ends, they stick to 0 when they hit 0. And Ito draw this function, okay, draw this function, and he said, okay, this is the first excursion. Then he looked for the second excursion and make the picture of the second excursion, and so on and so forth. Actually, this process is like process when with jump exit from 0, like my perturbation. And okay, this picture is nice when this measure is finite, but now assume that this measure is infinite. And in the most interesting examples, this measure is infinite. And you have infinite, but sigma finite. You have a lot of atoms, and you make some limit procedure. If this excursion is earlier than this excursion, then you have to draw this excursion earlier than this excursion. And he drew this excursion. Okay, there is not next excursion, but there is some definition. there is some definition and like excursions of Brownian motion. You have this excursion. Between these two excursions, there is another one and another one and another one, and so on and so forth. It proved that, well, if this measure satisfies certain properties, then this process is a Markov process, and it behaves outside of 0, like our initial process, like Brownian motion or alpha stable process. Well, this measure should be compatible in some sense with semi-group generated by our initial Markov process, a Brownian motion. And this measure P for process that we get has the following structure. We take measure eta dx, infinite measure, and so this is a measure on d0 infinity. And let me describe a process. At first, you select x, and then you start the process u alpha of t started from x, and then you stop it when you hit 0. And you select x not with this probability, not probability, but with this measure. So this is excursion measure for our process. And this measure equals c plus over x to the power 1 plus beta for positive x's dx, and c minus over x to 1 plus beta for negative x's. So if you consider excursion, for example, excursions that start outside of, say, fixed delta, then ratio of expected values of excursion that are above 0 to number of excursion that are below 0. So this ratio is equal to c plus divided by c minus. So this is my answer. So p divided by q equals c plus divided by c minus.
So the probability that the process
starts above 0 or starts below 0.
Let us suppose that it starts from 0. And
well,
which is the probability that at the instant of time t, the value of the process is positive.
Yes. And when you do all these calculations, it seems to me that no, sorry, no, I cannot say this. I cannot state this.
I propose you to calculate this.
Yes, I understand. No, I don't know the answer. I know that c plus divided by c minus equals to ratio of probabilities that excursion starts above 0 to the probability that excursion starts below 0. Our process, so there is no excursions that starts to 0. The picture is as follows, like this. Okay. If the process, say at the moment 0 is equal to 0, then there are a lot of heatings zero in any, there is infinite number of heating zero in any neighborhood of zero. And we have infinite number of very, very small excursions. So there is no first excursion. And every excursion, so we can say what is the beginning of every excursion, and the probability that the start of excursion is positive equals C plus divided by C plus plus C minus, and below C minus divided by C plus plus C minus.
This is a non-symmetric parameter for the process beta.
Yes, so this is analog of P divided by Q for skew Brownian motion.
Okay, and if may I to say a few words about my impression of it.
Okay.
My congratulations to the authors of these results. They have constructed something that really can be called skew alpha stable process. Many years ago, I tried to construct something that I thought should be called a skew alpha stable process, but I failed because in one of the situations, we obtained not a stochastic process at all, only pseudo process. And in the other my attempt, the speaker characterized that my attempt, and I should say that I don't think that the history is finished, because I think that one can construct another process that could be called a skew alpha stable process. I have one idea, but I would like to cite Professor Daletsky's words. He, many years ago, he once said, I have not had any proof yet, but I have firmly conviction. Yeah, thank you very much. I think that the presentation was excellent. Thank you.
Okay, thank you. Maybe some other comments, please. If there are no other comments, I also want to say a few words. Firstly, I have a question. Andrey, can you show us again this slide with the stochastic differential equation you obtained?
Yes.
This one, yes. So you started from the process U alpha. Then you get like a family of processes which are indexed by two parameters. And a natural desire can be just to avoid, exclude this beta. What happened when beta tends to 0?
When beta tends to 0.
So just if you want to eliminate beta, so you see?
No, if beta tends to 0, probably this process blew up.
Yes, then to alpha minus 1.
To alpha minus 1, I think that the limit will be u alpha. It seems to me. So this is my prediction.
So this is I just wanted because you use some semi-group theory and resolvents. I just wanted to exclude this beta by some limiting procedure to get something which depend only on you on alpha. Okay, I see. And the last one comment is I also have experience of communication with Daletsky, and he said to me one time that it is so nice that it must be true. So it was good talk, Andrey. Thank you.
Actually, here you can consider not only beta, but some. So we can characterize processes with the following resolvent, where eta is just a measure that satisfies some properties, and here you have to write a process with independent increments, Levy process with Levy measure eta. Yes.
I see. Okay. Okay. Thank you again. And who will be the next speaker? Georgi, maybe you know.
Next will be Naofil Salhi.
Okay, with multiple self-intersections. Okay.
Yes.
Thank you. Today we finish our work. Thanks everybody, and bye for the next week.
Goodbye.
Thank you. Thank you
Bye
for the
bye.
talk. Bye.